Welcome back. So in this chapter, we will discuss gradients, divergence, and curl, and also the Laplacian operator using sine functions. What do we mean by that? That is the likes of Einstein summation convention, Levi-Civita notation, and the Kronecker delta notation that we discussed at the beginning of this course. So we now see what is the usefulness of all of these two vector differential operations, and could they offer any help when it comes to vector differential operations. So the use of sign conventions, let's get to work. Use of sign conventions, or say sign functions to be precise. And you should know so far that nabla is the most important thing. So that means we should firstly see how do we define nabla using these sign functions. So we know, of course, that nabla is I del x plus j del y plus k del z. So we know that this can also be represented as k1, implying that we're using k1 instead of I, we will use k2 instead of j, we will use k3 instead of k. Okay, that means that instead of using I, J, K for the unit vectors, we'll be using K1, K2, K3. So this does not make any difference. What matters is what do they represent? What do these letters and symbols represent? That's what's important. So we can say then that this is K1 del X1. So we're using x1 in place of x, we're using y, we'll use x2 in place of y, and we'll use x3 in place of z. So this will be plus k2 del x2 plus k3 del x3. And of course, if we're going to write this using summation, we'll see that this is the summation from I equal to 1 to 3 of ki del xi. So we know that by summation, by this summation symbol, if we expand this over I, when I is equal to 1, we get k1 del x1. When I equal to 2, we get k2 del x2. When I equal 3, we get k3 del x3. So this is precisely a representation we can use. And by Einstein summation convention, since we know that we're dealing with vectors in space in three-dimensional system, we know that by default I should run from 1 to 3. And by Einstein summation convention, we can see that this subscript is repeated. That is, this is I right here, and this is another I right here. So we can let go of this summation symbol and just say that nabla is equal to ki del xi. And that is our definition of nabla here by Einstein's summation convention. Okay, so of course I is the what do we call this now? I is a dummy subscript or dummy index, as we have defined it previously. Okay, if you cannot remember that, please you can go back to that chapter where we discussed sign functions. Okay, so I is dummy subscript because obviously we can see that it is repeated. We have it appearing twice in a single term. Okay, so we know that when we come across something like this, it has to be expanded over from 1 to 3. So it doesn't make any difference to what we have here. Once we know already, we understand the Einstein summation convention. We know this is a dummy index because it appears twice in a single term, and with that, we are good to go. Okay, so that means with this, we can define the gradient. So we can define the gradient of a scalar field. So if we have a scalar field, gradient of a scalar field or scalar function defined by this a scalar field defined by this scalar function x1, x2, x3. That means this makes no difference. We're simply saying that instead of using x1, instead of using xyz, we're using x1, x2, x3. So it doesn't make any difference. That means if we're given a function that carries xyz, I want it to conform to this standard, we just use x1, x2, x3 in place of xy and z respectively. Okay, so that is the idea. So if we want to get the gradient of a scalar field, we know that by what we have done so far is nabla phi. So then we can write that as ki del phi del xi. Okay, that is simply ki del xi, which we have defined for nabla, then multiply by phi. So phi comes in front of that, so that will be del phi del xi. So that is how we define the gradient of a scalar field. Again, because I appears twice, it is still a dummy subscript and it should be expanded over from I equal to 1 to 3. So we know that by that this conforms with our definition that we have used so far. Of course, don't forget that the use of I here is arbitrary and K is just my choice. You might come across a material or you come across this in your textbook or notebook or lecture notes where I is being used. For instance, this could also have been correctly written as, for instance, IN or IM, then you have del phi del XM. It makes no difference. It simply means I is being used as a representation instead of K for the unit vectors. Okay, and M is being used as a subscript, as the dummy subscript instead of I for this expression of the Einstein summation convention. So it makes no difference. It expands out the same way and it gives us the same thing. So if you expand this, you will get I1 del phi del x1 plus I2 del phi del x2 plus I3 del phi del x3, which is exactly the same thing as this, except that we are using k instead of I. So that is exactly what that means. We should know you should know that there's some things here that are flexible because they are just representations, okay, which you could have chosen differently. Okay, so that means someone else also could write this as j, okay, m del phi, okay, let's use n for instance, and then use del phi del x n. So that also makes no difference. The only difference being that the person now chooses to use J for the unit vector representation instead of K or instead of I that we have used so far. So that is that about that. So just follow through and know precisely what we're talking about as we proceed. Okay. So now let's forget about all of these and just stick with use of Ki. Use of Ki and all of this here is strictly because that is what I am used to. So you might choose something different in your own notes. Okay, you might be familiar with something different or a different set of symbols. That is perfectly okay. What is important is that you understand the structure and you keep with it. So that's we're good. Okay, so let's go on now. And we have also discussed the divergence of a vector field. So if we have divergence of a vector field to deal with, how am I writing scalar and saying vector? So divergence of a vector field, okay, defined by some vector function phi. So we have vector function a. So in this case, this is vector function a, and we know normally we write vector a as a1 of x comma y comma z. So let's write that out, please. Okay, so this is a vector function. Of course, that will also depend on x1, x2, x3. Okay, so we know that normally we can write so this is what we want to deal with. We know we can write a vector from what we have done so far as a of x comma y comma z, and say that is going to be equal to a1, meaning the x component of that vector, which is also going to be by itself some function of x y z I, plus a2, which is also going to be some function of x y z then j, plus a3, which itself will be some function of x, y, z, and then k, because that is the z component. So that is fine from what we've been doing so far. Of course, you could also have written it as a sub x, a sub y, a sub z. That is also okay. So far, you know precisely what it means, and you don't mix it up with any other thing that could have been written the same way. You're good to go. Okay. So going forward, we know that we can write these as a1 of x1 comma y, sorry, x1 comma x2 comma x3. That is, we're using x1, x2, x3 in place of x, y, z. So we can write that as I. So instead of I, of course, we know we can write that as K1. Then plus same thing here, A2 of X1, X2, and X3. And we'll put here K2. Then plus A3 of x1, x2, x3, and then we put here k3. So this is perfectly okay. What has happened is that we have changed the symbol, so they still mean the same thing correspondingly, so we know precisely what we are dealing with. Okay, so with this, then it means that we can just literally write this as a I, okay, and k I. So we can write this vector as aiki. Why can we do that? We know this is also expanded from 1 to 3. So just like the subscripts of k are expanded from 1 to 3, we know that this is also expanded from 1 to 3. So we can use just a dummy subscript to represent that. So dummy because it appears twice. So this is I here and this is I here. So we know that has to be expanded from 1 to 3. So we can say A1 K1, A2 K2 plus A3 K3. And that's by our Einstein summation convention what we will write in this form. Okay, so that is that about the vector representation itself. So if we then have to do operate on or find, if you like, the divergence of the vector, then it follows that we will have, don't forget, divergence of a vector field A is given by nabla dot A. So if we will define nabla dot A, that means we will be looking forward to the use of nabla and A. So we have to use a representation for nabla, we have to use a representation for A. So now we know from this representation we have written nabla as ki del phi, ki del xi, and now we have also used the representation for A, which is ai ki. Okay, those two representations are perfectly okay, they're fine. Just that when we need to combine these two in an operation, it is best that we use different subscripts for each of the terms. So we know that del ai del ki del xi, which defines nabla, is different. That is, the terms of nabla are different from the terms of the vector function. So it is then best that we use a different subscript, that is a different letter for each of the definitions. Okay, so because of that, we can say, for instance, that we should let this vector function be equal to amkm. Okay, and or say ankn, and then just go with our definition of nabla, which we have established already, which is ki del xi. So that is fine. What's important is that we have to use different subscript for the two so that we can distinguish the terms of each of them. Okay, that is the idea. I mean, if you remember the examples we considered when we discussed sign conventions, also for instance, if we, when we wanted to prove some relation between vectors, arbitrary vectors a, b, c, we said let a be equal to ai ki, let b be equal to bj kj, let c be equal to something like cp kp. Why did we use all of that? So that along the line we could distinguish between the different components that are from the vectors a, b, and c. So that is the idea we will follow here as well. So because of that, so when I say that to obtain, right, so we now say to obtain div, okay, divergence of vector A, which we know already by definition is nabla dot A. We say let nabla be equal to, so we still stick with that ki del xi. So you could have changed this to, instead of I to m or n, that is fine as well, and then let A be equal to, okay, so I want to stick with this definition for uh, for the vector A. So let us use a different definition for this. So let's say this is km del xm. Then for A, we want to use aiki. Okay, so by that we can now go ahead and carry out our operation. So we now say that therefore nabla dot A will be equal to, so what is nabla? Ki del xi. So this is our vector dot the second vector, which is aiki. Why am I still writing I, please? I'm kind of just used to that. Sorry, please. We're using a different representation here, so let us put km del then xm. Yeah. So with this, we're good to go. We just follow the same process as we developed also when discussing sign conventions, which is the fact that we can bring the scalars of these vector portions together. We know that the scalar portion of this expression is del del xm. The scalar portion of this expression is ai. So all of these km and ki are what make all of each of these terms actually vectors. So we can put the vector portions together because that is where the operation should be happening. Okay, so we now say putting ai and this together, we know that is going to be del ai del xm. Then what do we have next? We have km, okay, dot ki. So we're good to go. With this, we can now simplify further and say that this is going to be del ai del xm, then km dot ki. From what we've done already, we know that is exactly what will give us the Kronecker delta. So sorry, am I writing del ig? That will be del delta m I, okay, in that order. So this is the Kronecker delta notation, and this is our result so far. Of course, we also have discussed the property or a property of the Kronecker delta notation is that when it shares a dummy subscript with any of the terms written with it, we know how it should behave. And by that, here, does this share a dummy subscript with any of the terms? Yes, you can see M is here and M also appears here, which means M is a dummy subscript since it appears twice in the same term. Okay, so in that case, M is shared with this and I is also shared with this. That means we can let go of the Kronecker delta and replace one of the subscripts with the other. Okay, so that is the idea. So if we're going to let go of the Kronecker delta, we can replace M with I everywhere we have it, or replace I with M everywhere we have it, because here M and I appear in both terms. So I mean M and I appear in the term written together with this, okay, or the expression or in the coefficient of the Kronecker delta notation here. And so by that we can write this as del A I. So I just want to keep I. So then M will be replaced with I, so that will be del xi, and that will be all for the Kronecker delta notation. This is a property of the Kronecker delta notation that we discussed, okay, when we talked about sign conventions. Please, if you cannot remember that, you should go back to that now and revise it. We explain how we came about that property, okay. So it shares a dummy subscript right here because this M appears twice, and one of them is on the Kronecker delta, one of them is on the other term, which is the coefficient of the Kronecker delta. So that is why we can let go of the Kronecker delta and replace M with I. So we could have done the same thing on I because I is also shared. It's a dummy subscript by this because it appears twice and it's also on the Kronecker delta. So we could have let go of I as well and replaced with M. So this could also have been del AM del XM. Literally, both will have the same meaning because these are subscripts and both of them are appearing twice in a single term, which means they are dummy subscripts that should be expanded over. So we have now established that therefore our nabla dot vector A, which is the divergence of vector A, is simply given by del AI del XI. So with this, we are good to go. Of course, if we would expand this, for instance, we know that this is a dummy subscript, this is II, which is a dummy subscript, so it should be expanded from 1 to 3 by our Einstein summation convention. So that means expansion of this would have given us del A1 del X1 plus del A2 del X2 plus del A3 del X3, of course, which is consistent with our definition so far, which says del A1 del X plus del A2 del Y plus del A3 del Z, because precisely that is what this means. We have said X1 is representing X, X2 is representing Y, and X3 is representing Z. So we know that this is reasonable, okay, and it is consistent with what we have so far defined, okay. So that is that about that. Let us now move on to the call of a vector field. What will be the definition for the call of a vector field? Okay, call of a vector field. So if we have a vector field, of course, defined still by some vector A, so we can say again, like we explained up there, that let A be equal to AI Ki. Okay, so for this also, we will let nabla be equal to, so we'll just use a different subscript just as we add it up there. So let's say Km del xm. So by this, we can now carry out the operation again and say that nabla, okay, so we now say that therefore the call or spin or rotor, if you like, of vector A will be equal to nabla cross vector A as we've defined it, and that will be nabla, which is Km del xm. So we'll take this Km del xm dot vector A, which is AIKI. And by this, we say that this is equal to, so we bring the vector portions as the scalar portions together and also the vector portions together. Sorry, please, this is not dots, please. That's a mistake. That is cross. Okay, so we know cross is multiplication, but it makes a different meaning for the vectors. Okay, so we're going to put the vectors together. We just multiply the scalars as they are. So that's what it's going to give us for the scalars. Del AI del XM. What else? We now have in bracket Km cross Ki in that order. Okay, so the order has to be kept too. So going further, we know this is going to give us del AI del XM. So this is del AI del XM, and then we have Km cross Ki. So from what we've done, that brings about the Levi-Civita notation or the alternating tensor notation, if you like. So by this, we'll have this to be equal to epsilon. So we keep to the order mi, then we introduce a new subscript. So we have not used j so far, so I'm going to use j for the third one, and then we'll put kj because this k has to have a subscript that is equal to the one we just introduced. So you could have used min here and used kn thereby. So that is the idea, and with this we are good to go. Do we have anything we can simplify here? The answer is no. Why? Because we don't have a critical delta here. We don't have any representation here. So if this is expanded, of course, we are 100% certain it to give us the same expression as what we had before. Okay, so you can play around with that as an exercise. Okay, so we know that nabla cross A would be equal to this representation. Okay, so that is that about that. So with this, we are good to go. That means you could have used or obtained a somewhat different in terms of subscripts now representation. If you used a different set of subscripts to define the vectors, yes, the vectors. So we know nabla itself is a vector differential operator. So you could have used, let's say, j for nabla and k for let's say m for this and then n for the next one. What's important is that you follow the order like that. So if you used m instead of, I mean, if you used what is it now, j for I, for instance, this would have been del hj del xm. That's if m was used for nabla, and this would have been in the other way around. So instead of m, yeah, m is still here. Instead of this I would have added j, and then we would not use j any longer. We would have to introduce something different, so n or m or whatever, or p or q, and then whatever we introduce to be the third one is what we'll go with the k that we have introduced here. So that is that about that. Don't worry, as we proceed, we'll play around with this and see how that can help us also simplify some proofs and actually establishing some vector differential relations. Okay, so now for now, that is all for the gradient of a for the call of a vector field. So let us see what would we get if we wanted to get the Laplacian. Okay, we know that the Laplacian operator is just an operator that can be operated on, okay, on a scalar field or a vector field, or a scalar function or a vector function, if you like. So how do we define the Laplacian operator? You should recall that the Laplacian operator. Recall that nabla squared, which was what we called it a Laplacian operator, and we said that could also be written as delta, was simply equal to nabla dot nabla. So if we will take nabla dot nabla, what would that be? Of course, again, we'll say let nabla be equal to, we choose whatever representation. So it's only nabla we have here, so let's just keep with what we already used to, ki del del xi. So this nabla is not different from this nabla. So it's not that we're using the first nabla to be ki del del xi and then use another representation for the second one. That will be absolutely confusing and wrong, and that will be nonsensical because these are not two different vectors. Okay, in the last two illustrations, nabla was clearly different from the vector a. So if we had a different vector b, for instance, we know that would be clearly different, so we would use a different subscript for it. Okay, but here we have nabla and nabla. Nabla is not different from nabla. Okay, so we're going to just go ahead and deal with this to see what it gives us. So it then follows that nabla squared, which we know to be nabla dot nabla, would be equal to ki del del xi, okay, dot another nabla, which is ki del del xi. So by this, we are good to go. So we carry out the same operation here. How do we do that? The scalar portions, will bring them together. That will be del del xi multiplying del del xi. Of course, that will be del squared del xi squared. Okay. Then we multiply by the vector portions, which is going to be ki. Sorry. The vector portions will give us ki dot ki. And of course, we know this is going to be del squared del xi squared, then ki dot ki. Of course, we know ki dot kj would have been delta ij, so ki dot ki is delta ii. So what is delta ii? So you might erroneously say that this should be 3 because of possibly one of the things we've done previously where we add delta we said that the ii would be because ii implies a dummy subscript. You might be tempted to say that this should be delta ii equal to delta 1 plus delta 2 plus delta 3 but that would be wrong. It will be a wrong thing to say because in this case delta ii is written with something else. That's a subscript. If delta ii was alone on its own, then we would simply say that delta ii is equal to 3. If it was just alone, that is, it has no coefficient, that is precisely just equal to 3. But now it is written with something else, and indeed we have the subscript even appearing here. So if we were to expand this, for instance, this will be del squared del x1 delta 1 plus del squared del x2 delta 1 delta 2 plus del squared del what do we call that now, del squared del x3 delta 3. So you can see that everywhere it appears, it is just going to give us 1 for each of those portions. So because of that, we can simply let go of this. We know delta ii is going to give us 1 all through, so we can forget about it and simply put in 1. Okay, so because of that, we simply write this as del squared del xi squared. So this is equal to 1, not 3, please. All right. So you might be wondering, does this really make sense? Because by now we know that nabla squared, which is the Laplacian, should be del squared del x squared plus del squared del y squared plus del squared del z squared, and that implies that we should go from 1 to 3. And now we have the way we have obtained this result, it's as though we have right here the subscript I appearing only once. And if it appears only once, that suggests that we have a free index and not a dummy index. I believe you still know the difference between these two. If this were a free index, that would not make any sense, because that would be implying that nabla squared, for instance, if we want to take nabla squared, it would depend on the particular number we're interested in or the particular components we're interested in. No, nabla squared itself should expand to 3. So this should have been some dummy subscripts, but now it appears only once, and our convention requires that it should appear twice for this to be a dummy subscript or dummy index, if you like. Now, what you should know about this symbol, even though we will retain the representation like this, is the fact that this is squared. And how did we come about this? We came about this by multiplying, look at it here. We came about this by multiplying del del x with del del x, del del xi with del del xi. So, literally, we could have retained this as del del xi then of del xi, so that you know that I actually appears twice inherently. So even though this has been put together as xi squared, we know that I appears twice, okay, in this. So this is still a dummy subscript. So, and this representation is precisely what we use for the Laplacian. So our Laplacian delta or nabla squared is simply del squared del xi squared. Okay, so we know that xi squared xi is appearing twice. Okay, that means the subscript I appears twice, which means this is a dummy subscript as we know it, and of course it should be expanded from 1 to 3, which implies then that basically, as we have obtained here, nabla squared would have been del squared del x1 squared, okay, plus del squared del x2 squared plus del squared del x3 squared. And with this, we're good to go. We know it is consistent with what we know, okay, already, which is del squared del x squared plus del squared del y squared plus del squared del z squared. So that's precisely what we have now obtained, and life is as good as that. So if you want to operate this on a vector, you're good to go. Just place the vector here. Want to operate this on the scalar, you're still good to go. Place the scalar here. And that is that about the Laplacian operator defined in sine functions. So that is the end of this lesson. I'll see you in the next one as we consider some examples, okay, the next few lessons of this chapter on the use of sine functions. So we now carry out some actual operations or some actual problems, okay, using all of the things that we have now learned in this lesson. So I'll see you in the next lesson. It's an interesting one. Thank you for watching.